Welcome! In this session, we'll dive into the problem next closest time. This is an intriguing challenge that tests your analytical thinking and problem-solving skills, particularly around time manipulation and digit reuse. Let's explore the problem and uncover the best approach to solve it. In this problem, you're given a string representing the current time in the 24-hour clock format HH/mm. Your task is to determine the next closest time that can be formed using only the digits in the given input. Importantly, you can reuse the digits as many times as necessary, but the resulting time must still conform to the 24-hour clock format. This means the hours must be between 00 and 23, and the minutes must be between 00 and 59. For input, you will always receive a valid string in the correct format, and your output also needs to be a valid time string in the same format. The goal is to find the next closest valid time that is greater than the current time, wrapping around to the beginning of the next day if necessary. Let's look at an example. If the input time is 1934, the digits available to form the next time are 1, 3, 4, and 9. To find the next closest time, we consider all possible valid combinations of these digits. The nearest valid time after 1934 is 1939, which uses the same digits. Notice that 1940 is not valid because it includes the digit 0, which is not part of the input digits. Now consider another example where the input is 2359. Here, the available digits are 2, 3, 5, and 9. The next closest valid time is 2222. Even though midnight is valid, it is farther away in time compared to 2222, so 2222 is the correct answer. In the second example, we saw how the solution must prioritize the closest time that can be formed using the available digits, even if it means reusing the same digit multiple times. For a third example, if the input is 132, the available digits are 0, 1, 2, and 3. The next closest time is 133, as it uses the same digits and is the smallest possible increment from the current time. Also, note that the solution must comply with the constraints of the 24-hour clock to ensure the generated time is always valid. For instance, 25:00 or 12 hours 60 minutes would be invalid. There are a few important edge cases to keep in mind. First, if the input time consists of the same digit repeated, such as 1111, the next closest time is the same, since all possible combinations of the digits result in the same time. Second, when the solution involves wrapping around to the next day, such as from 2359 to midnight, this must be handled correctly. Lastly, the algorithm must ensure that no invalid times are generated, meaning values like 25:00 or 12 hours 60 minutes must never appear. These edge cases highlight the importance of carefully validating and generating times using only the input digits while adhering to the constraints of the 24-hour clock. To solve this problem, we explored multiple approaches. The first is the brute force approach, which is straightforward in its intuition. Here, we generate all possible valid times using the digits from the input string. For example, if the input time is 1934, we extract the digits 1, 9, 3, 4, and create all combinations of 4 digits. From these, we filter out any invalid times, like 25:67, leaving only valid ones. Once we have this set, we compare each valid time to the input time and identify the next closest one. If no valid time is greater, we simply wrap around to the smallest valid time. This approach works, but it has a time complexity of 256, since we generate 4 to the power of 4 combinations and validate each in 1 time. While the brute force method is simple and easy to implement, it can feel inefficient because of the exhaustive generation of combinations. Another approach we considered is the optimized iterative approach. This avoids generating all combinations upfront and instead increments the current time minute by minute, checking at each step if the new time can be formed using the input digits. The iterative approach is more efficient in handling this problem. In the worst-case scenario, we might need to check all 1440 minutes in a day. However, since validating each increment time is computationally cheap at 1, the overall complexity is 1440. This makes the approach manageable, even for real-time applications. It is also more space-efficient, as we don't need to store all possible combinations of times. Another strategy we examined is the recursive backtracking approach. Here, we construct valid times digit by digit, pruning invalid paths early. This method involves recursively building hours and minutes using the input digits, then comparing each valid time to the input to find the next closest. While this approach avoids explicitly generating all combinations at once, it still has a complexity of 4 to the power of 4, due to the recursive nature of the generation process. The trade-off is that, although it avoids some redundancy, it remains less efficient than the iterative approach and can be harder to debug. Ultimately, we chose the optimized iterative approach as our solution. This method strikes the right balance between simplicity and efficiency, leveraging the problem constraints effectively. The key realization here is that there are only 1,440 possible times in a day, which makes iterating minute by minute a feasible strategy. Additionally, checking if a time can be formed using a fixed set of digits is computationally cheap. By focusing on the incremental progression of time and using modular arithmetic to handle the 24-hour clock, this approach avoids unnecessary computations. Compared to brute force, it skips the generation of invalid combinations, and compared to recursive backtracking, it's more straightforward and easier to debug. The iterative approach is intuitive, efficient, and well-suited for this problem, making it the most practical choice for determining the next closest time. To solve the problem of finding the next closest time, we start with the given string time in the format HHMM. Our goal is to determine the next valid time that can be formed using only the digits from the input. For example, if the input is 1934, we can only use the digits 1, 9, 3, and 4 to construct the new time. The first step is to extract these digits by parsing the string and storing them in a set. This gives us a reusable pool of digits and ensures quick lookup during the algorithm. Next, we convert the input time into total minutes since midnight. By transforming HHMM into a singular value, such as 1174 minutes for 1934, we simplify the comparison process when searching for the next closest time. This step is critical as it allows us to handle time calculations more efficiently. Now that we have the pool of digits and the input time in minutes, the next step is to generate all possible valid times using these digits. By forming all 4-digit combinations from the pool, we create potential candidate times in the format HHMM. For each combination, we verify its validity by ensuring that the hour lies between 0 and 23, and the minutes lie between 0 and 59. Valid times are then stored as total minutes, which makes them easier to sort and compare. Once we have all valid times, we sort them in ascending order. To find the next closest time, we locate the position of the input time in this sorted list and select the next element. If the input happens to be the largest time in the list, we wrap around to the smallest time. Finally, we convert the total minutes of the next closest time back into the HHMM format by calculating the hours and minutes and formatting them as 2-digit strings. This algorithm is built on several key insights that make it both intuitive and efficient. First, the ability to reuse digits from the input string means that the pool of digits remains constant throughout the process, simplifying the logic. Second, wrapping around to the smallest time when the input is the largest can be elegantly handled using modulo arithmetic or by appending the smallest time to the list of valid times. Lastly, by focusing only on valid times and sorting them, we streamline the process and avoid unnecessary computations. From a data structure perspective, we use a set to store the pool of digits, ensuring efficient lookups, and a list to store valid times for sorting and comparison. The complexity of our approach is manageable because generating all 4-digit combinations results in at most 256 possibilities. Filtering valid times and sorting them is computationally inexpensive, making the overall complexity effectively constant for this problem since the input size is fixed. Finally, let's address some edge cases that the algorithm handles seamlessly. If the input time is the largest valid time, such as 23:59, the algorithm correctly wraps around to the smallest valid time, ensuring the solution is always valid. For cases where all digits are the same, like 11:11, the algorithm generates only one valid time and appropriately identifies it as the next closest time. It also handles invalid time combinations, such as 25:61, by filtering them out during the generation step. These considerations ensure that the algorithm is robust and covers all potential scenarios, providing a reliable solution to the problem of finding the next closest time. This solution efficiently calculates the next closest valid time using the given digits. First, the digits are extracted from the input time and sorted to facilitate comparison. The current time is converted into minutes for simpler arithmetic operations. A loop is then used to iterate minute by minute, wrapping around after 24 hours. For each iteration, the next hour and minute are calculated and formatted into the HH/MM string. The program checks whether all characters in this new time are part of the original set of digits. If so, the time is returned as the next closest valid time. This ensures correctness while maintaining efficiency. Here, we begin by importing the necessary Java utilities and defining the main solution class. The goal is to find the next closest time using only the digits present in the current time. To start, we extract the unique digits from the input string. This is done by iterating through each character in the time string and adding non-colon characters to a hash set. Since sets don't allow duplicates, this ensures that only unique digits are collected. Next, we convert this set into a sorted list. Sorting the digits allows for easier iteration when we need to compare combinations later. After that, we calculate the current time in minutes. We do this by extracting the hours and minutes from the time string, converting them to integers, and combining them into a single value representing total minutes. This conversion simplifies the process of incrementing the time. Finally, we set up a loop where we'll increment the time 1 minute at a time, ensuring it wraps around after 24 hours. This prepares us for the next step, checking if the new time can be formed using only the original digits. Now, we format the increment time back into the HH/MM format using the string.format method. This ensures the time string maintains its proper 2-digit format for both hours and minutes. The next step is to check if the formatted time can be constructed entirely using the digits from our original list. We achieve this by calling a helper method, isValid. Inside this method, we iterate through each character in the new time string. For any character that isn't a colon, we verify if it exists in the list of original digits. If we encounter a character that isn't in the list, we immediately return false, indicating the time is invalid. If all characters pass the check, the method returns true. Once a valid time is found, it is returned as the result. This ensures we only select the next closest time that can be formed using the original digits, completing the solution. To solve this problem, we start by analyzing the input time, which in this example is 1934. First, we extract the unique digits from the time, ignoring the colon. The digits are 1, 3, 4, and 9. For convenience, we sort these digits into the list 1, 3, 4, 9. Next, we convert the given time into the total number of minutes since midnight. Since there are 19 hours and 34 minutes, we calculate this as 19 times 60, plus 34, which gives us a total of 1,174 minutes. Now, to find the next closest valid time, we increment the time minute by minute. Each time we increment, we convert the new total minutes back into hours and minutes and check if the digits in the resulting time only use the given set of valid digits. For instance, after 1 minute, the time becomes 1935, but the digit 5 is not in our set of valid digits, so we continue searching. As we proceed, each minute is tested to see if all its digits are valid. For example, after 2 minutes, the time becomes 1936, but the digit 6 is not in our set of valid digits, so we keep going. After several increments, we reach the time 1949, which is 1,194 minutes from midnight. Converting this back to hours and minutes gives us 19 hours and 49 minutes. This time only uses the digits 1, 9, and 4, all of which are in our valid set. Therefore, 1949 is the next closest valid time, and we return it. Moving to the second example, the input time is 23:59. From this, we extract the digits 2, 3, 5, and 9, which are sorted into 2, 3, 5, 9. Converting 23:59 into total minutes gives us 1439 minutes. This is the maximum number of minutes in a day, so when we start searching, we must wrap around to the beginning of the next day after midnight. Here, the search begins by incrementing the total minutes and wrapping around at 1,440 minutes. When we increment from 1439, the next minute is 0, which corresponds to midnight. However, the digits in midnight include 0, which is not in our valid set. So we continue searching. After another increment, the time becomes 001, which also includes the digit 0, so it is not valid. This process continues until we reach 151 minutes from midnight, which corresponds to 2:35. At this point, we find that all the digits in 2:35, namely 0, 2, 3, and 5, are part of our valid set. Therefore, we return 2:35 as the next closest valid time. Now we move on to the final example, where the input time is 1:32. For 1:32, we extract the unique digits 0, 1, 2, and 3, and sort them into the list 0, 1, 2, 3. Converting this time to total minutes gives us 92 minutes, since 1 hour is 60 minutes, and we add 32. To find the next closest valid time, we increment this value minute by minute. After one increment, the time becomes 93 minutes, which corresponds to 1:33. Checking the digits in 1:33, we see that they are 0, 1, and 3, all of which are in our valid set. Since this time meets all the criteria, we return 1:33 as the next closest valid time. Here, we analyze the time complexity of the solution. The algorithm starts by extracting the unique digits from the input time and converting the current time to minutes. Since the number of characters in the input is fixed at 5, both these operations take constant time, or O1. Next, the core of the solution is a while loop that checks every minute in a 24-hour period to find the next closest valid time. Since there are 1440 minutes in a day, the loop runs at most 1440 iterations. Within each iteration, operations like computing the next minute, formatting it into the HHMM format, and checking if all characters are valid digits all happen in constant time because the structure of the input and operations on it are fixed. Therefore, the time complexity per iteration is O1, and across all 1440 iterations, it remains linear in the number of minutes, O1440. However, because 1440 is a constant value, we can simplify this to O1. Now, let's consider the worst-case scenario. Even if the algorithm iterates through all 1440 minutes in a day, the total time complexity is still O1440, which simplifies to O1, given that 1440 is a constant. For the space complexity, the solution uses a small, fixed amount of memory. The set of unique digits extracted from the input contains at most 4 digits, which takes O1 space since the input time is fixed at HHMM. Additionally, variables such as current_minutes, next_hour, next_minute, and next_time each occupy constant space. No dynamic data structures or additional memory allocations are needed. Therefore, the overall space complexity of the solution is O1. Let's compare this optimized approach to a brute force solution. A naive approach might involve generating all possible valid times using the 4 digits from the input, which would require iterating over 4 digits for each position in HHMM. This leads to 4 to the power of 4, or 256, total combinations. From there, we would filter out invalid combinations, such as hours greater than or equal to 24 or minutes greater than or equal to 60, and sort the remaining valid times. The sorting step introduces additional overhead, making the brute force time complexity O, 4 to the power of 4 plus k log k, where k is the number of valid times. In contrast, the optimized solution avoids generating all combinations and instead iterates through the 1440 minutes in a day while checking only valid times. This reduces the time complexity to O1, as the number of iterations is constant. Additionally, the space complexity is also O1 due to the lack of dynamic storage requirements, making the optimized approach significantly more efficient than the brute force method. Finally, let's break down the best, average, and worst-case scenarios for this solution. In the best case, the next valid time is found on the first iteration, such as when the input is 2359 and the next closest time is 2222. Here, the complexity is O1. In the average case, the solution finds the next valid time after checking a fraction of the 1440 minutes, but the total time complexity remains O1, because the number of iterations is capped at a constant value. In the worst case, the solution checks all 1440 minutes before finding the next valid time, yet the complexity is still O1 for the same reason. In conclusion, the optimized solution is highly efficient, with constant time and space complexities of O1. This is a significant improvement over the brute force approach, which has exponential growth in time complexity due to generating all possible combinations of digits and performing additional filtering and sorting. When tackling this problem, there are several common mistakes to watch out for. First, not handling time wraparounds correctly can be a major issue. For example, if the current time is 23:59, the next closest time might be midnight on the next day, but failing to account for this will result in an incorrect solution. Another common pitfall is ignoring invalid times, like 25:67 or 12 hours 89 minutes. These values don't fit within the 24-hour clock format, and allowing them into your solution will lead to errors. Overcomplicating how you select digits is another mistake to avoid. Generating every permutation of digits using excessive loops or recursion is unnecessary and makes the implementation more complex than needed. Finally, it's important to compare times correctly. Treating hour and minute values as a single numerical entity, like 1234, can lead to incorrect comparisons because the formatting of time doesn't align with simple numerical values. Instead, time should always be handled in the hour and minute format to maintain accuracy. Next, it's essential to optimize for edge cases. Scenarios like all digits being the same, such as 11:11, or a time close to midnight, like 23:59, often trip up solutions that aren't robust. Ignoring these can leave your algorithm incomplete. Now, let's consider some insights for interview scenarios. Problems involving time typically require a strong grasp of valid ranges in modular arithmetic, since time wraps around after 23:59. Focus on understanding how to validate time and iterate efficiently over possible combinations. A great optimization strategy is to increment time minute by minute while keeping the digits constrained to a predefined set of allowed values. This avoids the overhead of generating all permutations. Additionally, in an interview, it's crucial to clearly explain edge cases like wraparounds and invalid times. This demonstrates not just technical ability, but also a thoughtful and comprehensive approach to your solution. Now, let's explore related problems that share similar concepts or techniques. LeetCode 681, the next closest time problem itself, asks you to find the next closest time using the same digits, which is our focus here. LeetCode 36, Valid Sudoku, involves validating constraints within a grid, which parallels how we validate time constraints. LeetCode 267, Palindrome Permutation 2, requires generating valid permutations under specific constraints, a concept that overlaps with generating valid times using a fixed set of digits. Lastly, LeetCode 31, Next Permutation, deals with finding the next lexicographical arrangement of a sequence of digits, which is similar to the idea of finding the next valid time. Familiarizing yourself with these problems can help you build transferable skills and deepen your understanding of related patterns. Finally, let's discuss alternative approaches and their trade-offs. One approach is brute force permutations, where you generate all possible valid times from the given digits and sort them to find the next closest time. While simple to implement, this approach is computationally expensive because you're generating four permutations and validating each one. A more efficient method is incremental time generation. Here, you start with the current time, incremented minute by minute, and check if the resulting time uses only the allowed digits. This approach is highly efficient, requiring at most 1440 iterations for all the minutes in a day, but it demands careful implementation to ensure time validity. Another option is the mathematical modulo approach. This involves using modular arithmetic to handle time wraparounds and validate times. While this method is elegant and efficient, it requires a deeper understanding of modular math concepts. Each method has its trade-offs, so choose the one that best fits the problem's constraints and your familiarity with the techniques. Great job following along. To wrap up, we reviewed the next closest time problem and discussed a brute force approach to solve it. This problem emphasizes key concepts like digit reuse and handling edge cases. Thanks for watching, and be sure to like and subscribe for more content. Keep practicing and stay curious. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!